Okay, great. Okay, so good evening, everyone, and welcome to this verification seminar, series seminar. So today it's a pleasure to have Ilya Sergey from National University of Singapore. Ilya is an associate professor there, and his broad areas of interest are in programming languages, software verification, and distributed systems. Okay, so today Ilya will be telling us about verifying distributed systems in Lean. So over to you, Ilya.
All right. Yeah. Thank you so much, Deepak. Okay, so it's my great pleasure to be here, and thank you so much for inviting me. I'm going to talk about the topic that I personally find very exciting. This is something that my team and I have been working on for more than 2 years. And well, overall, I've been looking at verification of distributed systems for the past 10 years or so. And now I think we are very close to have something that is a universal solution to this very challenging problem. All right, so there is also a couple of buzzwords in the title, such as multimodal verification, and this is something that is going to be a significant topic in this talk, and I'm going to explain what I mean by that, but we will come to that later. Okay, so, and I have to say that obviously this is the work that has been done in collaboration with many brilliant PhD students that I have. Most importantly, Georgia Perle, Vova Gladstein, Helad Kinsberner, and Chuan Zhao. All right, so distributed systems, and why do we care about that? So, well, this is the framework that I'm going to present, but distributed systems or distributed protocols are a very important class of algorithms. So these are the algorithms that we rely on every day. We rely on them right now because we are running Zoom and we are having this remote meetings between, and obviously the coordination and the transfer of data is something that is orchestrated by a distributed protocol. So these protocols are the algorithms that define how multiple different parties, usually referred to as nodes, collaborate with each other in order to achieve a common goal. And from the theory perspective, it's a very old problem. So, many of you probably know from the college this classical paper by Lamport on the vector clocks, and also problems such as distributed algorithms for mutual exclusion or for transaction commits. So couldn't find canonical reference for a two-phase commit. So here's a picture from Lamport's lectures on the verified distributed systems. So what makes this class of protocols particularly intricate is the sheer number of moving parts and the fact that you cannot really think about them sequentially as step by step, because many things can happen non-deterministically, and obviously the state space of possible executions is very large even for the simpler instances of these protocols. So, but what makes them even more complicated is the fact that many things can go wrong during the execution, because we live in the complex world. Some of the parties might just stop acting, or some nodes might fail. And for that reason, the humanity has designed a family of what's called fault-tolerant distributed protocols. The most famous ones include view-stamped replication by Brian Oki and Barbara Liskov. So that's the same Liskov as Liskov substitution principle. And obviously, what could we do without Lamport? So he truly invented most of the important things in this area, and also later, as we all know. So the part-time parliament is a classical paper on what's called Paxos consensus protocol, with a very cute fable that explains how the algorithm works. And many more protocols for fault-tolerant distributed agreement and distributed communication have been published since then. I'm not gonna show all the papers. I'm just going to show like some of the most representative or more recent ones. So, and if you think that this is where the complexity ends, well, that's wrong, because there's even more things that can go wrong. For instance, some of the parties might just outright act maliciously, and this is what we call Byzantine protocol. So again, well, you guessed it, the name is coined by Lamport, and who compares the problem of designing a distributed system in which some nodes might just fail to cooperate and try to thwart the attempts of other nodes to reach reach the desired results. So he compared it to the problem of different generals in the Byzantine and ancient Byzantine army who try to communicate by sending messengers, but they cannot see each other, and they're trying to coordinate whether they should like attack besieged city or they should retreat. And some of these generals might be traitors, so like how to make sure that the honest majority of the generals, because if it's not the majority, then there is absolutely no chance. But if there is a majority, how to make sure that they still come up with the uniform decision, they come to a consensus. And again, this is just such an important problem that initially it was coined in the context of fault-tolerant data meter reading in avionics, but later it found lots of application in. So yeah, here's another very famous protocol for this PBFT by Castro and Lisco. So yeah, so this problem is something that found a lot of application in the modern financial technology, think blockchains, but not necessarily even banks. Traditional banks, they utilize these protocols, and this is why there are many more of these protocols designed with the goal to optimize for particular scenarios, for particular latency constraints, while all preserving the same idea that the honest majority of cooperating nodes still needs to reach the consensus. So this is just to give you an idea that the space of distributed protocols is very large. And even with what I've shown, I've only shown a small slice of what's available there. So these are very interesting algorithms. And when there is an interesting algorithm, there are always people who want to like reason about these algorithms. So why do we want to verify distributed protocols? Well, because surprisingly, quite a few things can go wrong, and not just in the implementations that might be buggy, but in the protocols themselves. So George, who is one of the co-authors in this work, maintains this list of publicly disclosed bugs in classical distributed protocols, and this list actually keeps growing. Many people contribute. So bugs are typically violations of two classes of properties. So safety properties, I mean bad things will not happen, and this is something that all of you know as just like traditional program correctness. In a sequential world where we think about algorithm being correct or being wrong, we think about them in terms of safety properties. Liveness properties is something that only happens in a concurrent or distributed system. Well, I mean, it might happen in ordinary programs, but then it's kind of easy to detect. It just means the program doesn't terminate. But if you have a concurrent system or distributed systems, liveness properties or their violations, they might be much more interesting. For example, the system might function as a whole, but certain things might never happen to it. Or it might, for example, reach a deadlock where nothing bad happens, but the system just fails to make progress as a whole. And this is something that we know in the concurrent world. So an analogy that I like to give in the class when I teach concurrent and distributed systems is that if you think of just a single node system being an elevator, so the safety properties means that the elevator doesn't crash or doesn't stop and open the doors between the floors, because that's obviously unsafe. And liveness property means that if you press the button, the elevator will eventually come to your floor. So there will be no scenario when you're just waiting for the elevator forever. So safety property is something that can be reliably detected by conventional black box testing. So we run the system, and if it crashes, that means, or it violates the properties, that means that the bug has been found. It's much more difficult to test for liveness properties unless you have some insight into the system's internals, and you can spot some internal repeating states, because if you test for liveness, basically your property is invalidated by an infinitely long execution, and if you think that it has been violated, or maybe you just haven't waited long enough. So this is why reasonable liveness is quite interesting. Okay, so when it comes to verifying safety and liveness of distributed protocols, obviously people looked at it, and for at least 20 years, probably more. So the early efforts to formalize systems in what's considered to be modern proof assistance go back to 2005, but I'm quite sure this is not the very first reference. I'm sure there are even from before that. So people looked at building ways to verify safety and liveness properties of distributed protocols, and pretty much any significant proof assistant, and sometimes they build proof assistants just for that. So the list goes on and on and on. So there are quite a number of tools, and obviously each one, I mean, I deliberately put some of them with my name on it. So each of these papers position themselves as a tool of choice for verifying safety or liveness properties of distributed protocols. And one thing that all these tools have in common is that, well, no one really uses them. And I wouldn't be too surprised if just looking at this slide, you do not recognize any of these papers, because this still remains a niche. And the reason for that is not the lack of soundness or correctness of this tool. It's just very, very bad ergonomics. So researchers, they focus on the correctness and the novelty, but in doing so, they typically do not optimize for usability of the tool. So when it comes to usability of a tool for verifying distributed protocols, what really takes the cake is actually one of the simplest tools, and this is TLA+. So TLA+ is a specification language which comes bundled with effectively exhaustive testing framework or explicit state model checker. And this is initially also by Lamport and by a number of people at Microsoft Research who developed it over the course of the last 25 years. And initially it was very unpopular, but when people started to take some real interest in verifying distributed protocol designs, they realized that this is pretty much the only game in town, and this is the only tool that works and detects bugs quite reliably, even though it doesn't give 100% guarantees that your protocol is bug-free and satisfies the safety property. So the way TLA Plus works is actually like very easy. So the engineer, so here's an engineer, writes the protocol specification and writes the property that they think the protocol should satisfy. And then it runs the exhaustive testing using the tool called TLC that ships with TLA Plus. And TLC is very good at breadth first traversal of the reachable state space from the initial states of the system. And then typically it either exhausts the state space up to a certain depth and says, well, you know, up to certain depths, it's all right, or it comes up with counterexample. And oftentimes people even instantiate the model with parameters that make the state space finite. So you can prove that your protocol is correct for a certain finite instance. Obviously, like you can prove that it's correct for 5 nodes, but obviously it doesn't mean that it will be correct for 6 nodes. So that's why we use symbolic methods. So, but symbolic methods come with a cost. So the problem is that if you take something like TLA+, you actually manage to get a lot of benefit with a relatively short time investment. So 1-2 days, nowadays probably 1-2 hours, probably even less, because you know the lamps are just very good and auto-formalizing everything in any conceivable tool. And you already have the design of your system prototyped, and you have the properties, and you get some quick feedback. Well, back in the days, and by back in the days, I mean a year ago, people actually were very serious about committing to a particular tool because that largely affects how you're going to interact further. So you start with something like TLA Plus that allows you to... Sorry, someone says something to ask? Yeah.
What do you mean by concrete state? Maybe you were going to explain. What do you mean by concrete state in concrete state model checking on the slide?
Okay, so what is your background?
Excuse me?
What is your background? So I could answer this question at the right, using the right vocabulary.
No, I've done verification. I've done protocol verification. So I have a verification there. So I know concrete state versus abstract state. I thought all these were abstract models of the actual protocol implementation. That's why I was curious. Is this, concrete state versus abstract state? I understand that. Okay, if you have an abstract model, then there is an actual implementation. I usually people use the term concrete state as something distinct from abstract state. That's why I was I wanted to check with you as to in what context you use.
Okay, so the answer is very simple. Concrete state means that the state space of your system is represented by a set of instances of a data type. So concrete state means that it's an array or a record, something that corresponds to a data type in the program. As opposed
if
to...
I may intercept.
Okay, sure.
But essentially, it's still an abstraction of the actual protocol that is implemented, right? This is all happening within a model of TLA+. So the concrete state is still not concrete in the real world sense. It's still within the model of what TLA+ can model.
I'm not sure I understand the question. It's very concrete in TLA+. It's a data structure. But since you didn't let me finish the sentence.
Okay.
As opposed to it, as opposed to concrete state, there is a symbolic state where the state space of a system is represented by a logical formula. So rather than a set of data types.
Okay. So you mean explicit state. Okay. So
Yes.
yeah. Okay.
Mm-hmm.
As opposed to sets of states represented by formula.
Mm-hmm. That is right.
Okay, thanks.
All right. So when it comes to, well, since now the right question has been asked about the concrete or explicit state, we also have symbolic state representation, where you actually can verify your system for an arbitrary size of the model by reason about its symbolic. And there are tools that do that. For example, Ivy is a relatively famous tool that compiles the system description and its properties to SMT-lib, so the language that allows to express first-order logic formulas and then check their satisfiability or unsatisfiability. It's a really nice tool. The problem is that it comes with limitations that when your system specification and the property fall into decidable fragment of the first-order logic, you can have the proof of your property. But if they do not, then chances are the SMT solver will just time out. So decidability is really problematic. So you can pick a more expressive tool, such as Daphne, which is still SMT-based, so it works in first-order logic, but Daphne provides an expressive language to define heuristics of how you prove your or disprove your formula. So you can select triggers, you can provide additional lemmas, you can control your theories. It takes some time to master, but you can actually increase the expressivity of your specification and go all the way to very complex systems, and that has been demonstrated by several efforts. The most notorious one is Ironfleet by Microsoft. Finally, if you want to verify the system for the properties that require, for example, reasoning about nonlinear arithmetics or probability, just something that doesn't fit so well into the first-order logic, you can pick your favorite proof assistant based on the higher logic, such as Rock or Isabelle or Lean. Nowadays, Lean is one of the most popular. And there is quite a number of frameworks, so I picked one. So Growth, that's a framework that allows you to implement a distributed system and verify it for a whole bunch of very non-trivial properties. But in the pre-LLM era, it took many person-months to develop a proof for a single protocol. And the problem is not that some tools are more difficult to use than the others. The problem is that the whole space is very fragmented. So effectively, if you are committed to a single tool, it makes it very difficult to migrate to another one without re-implementing the whole system from scratch and occasionally using very different vocabulary and very different abstractions. For example, the modeling language of Ivy is something that people in general find very difficult to master. But even though it gives you lots of benefits if you manage to express your system and its properties in its terms. So when the tool is not sufficient, well, people either use a combination of tools. For example, they prove some properties in Ivy and some properties in Isabelle Poe, or you patch the tool and add an escape hatch that allows you to increase its expressivity. And that happened to all those tools. So TLA Plus has a very rudimentary proof mode that some people use, but many people don't even know that it exists. Ivy, Daphne, they all have some way to write a sort of mathematical proof, but obviously they are very limited compared to the general purpose mathematical proof assistants such as Rock or Isabelle or Lean. And this is a scenario that seems to be repeating over and over. People decide to build a verifier for a problem that they're interested in, and then there's a sunk cost, so they want to keep using it. And then they realize that, well, they need to extend this verifier. And with that, the code base grows, the trusted component grows, because the larger your verifier, the larger is the surface for bug, and the transfers your verifiers and so on. So it's not a very good situation. Also, and this is what contributes to the whole fragmentation of formal verification space. So I'm sure like many people on this talk have implemented at least one verifier in their life, and maybe this is something that they still support, but I think we can all agree that it would be nice if we could bring all these tools together. And this is this is not the thesis with which we went into this agenda of building yet another tool for verifying distributed protocols, but this is what we ended up having, and I'm very happy that things came up this way. Okay, so this is George. He is my PhD student, and while working on yet another iteration of building yet another verifier for distributed protocols, he came up with this kind of tongue-in-cheek homage to a very famous, rule, which I'm going to refer to as Perlet's law. And the thesis is as follows. So every verifier expands until it contains an ad hoc, bug-ridden, and usable implementation of half of the interactive theorem prover. So some of you might recognize that this is actually a paraphrase of a famous Greenspoon's 10th rule, which roughly says that any sufficiently complex program in Fortran or C contains buggy suboptimal implementation of half of the interpreter for common Lisp. The follow-up is that those verifiers which cannot so expand are going to be replaced by those that can. And this is kind of a trend because each verifier ultimately wants to become a general reasoning framework, and those that cannot do so because people move on and stop maintaining them, they eventually just drop, and no one really remembers about that. So this is one of the observations that we have summarized in this workshop paper from earlier this year, but there are obviously more technical takeaways of trying to build yet another verifier. So our solution to this problem was actually not to build a standalone verifier. It was to build a library in deliberately one of the most powerful and expressive frameworks for mathematical reasoning. And for that reason, we picked Lean. So initially, we just were curious what Lean is, and it turns out that was a really good choice because Lean is very extensible and allows to implement a lot on it, not as a library. So that's how we developed Whale. So Whale is a verifier for distributed systems that actually allows to do all these things that TLA Plus and Ivy and Daphne and Grove allow you to do. And I'm going to tell you how to do that. But most importantly, the reason why we managed to get all these ways to validate distributed protocols is just because we built this verifier as a library in Lean. Okay, so probably this is quite redundant because this is a formal verification seminar, but let me just give a very quick overview of what Lean is. So this is an interactive theorem prover. It is also a programming language. It's a functional language. Think something like Haskell or OCaml. So Lean and its tooling, they are bootstrapped in C++, but most of the ecosystem is already implemented in Lean. And automation and libraries and even the compiler itself, it's all Lean. It's very extensible. It has the best, one of the most powerful macro programming systems, probably compared just with Racket. And it has very nice integration with VS Code. It has lots of techniques for proof automation and integrates nicely with SMT. And most importantly, actually, all this infrastructure, it sits on a very small trusted type checker, which is responsible for checking proofs. So the rest of the ecosystem is just to improve the quality of life. But when it comes to checking the proofs, it's a matter of just a few hundred lines of code, which have been implemented in multiple instances, differentially tested. So this is a piece of program that is largely believed to be bug-free. And importantly, Lean is not going away because there is a whole quite well-funded non-profit organization called Lean for All, which is responsible for maintaining it. So the reason why you might have heard of Lean is because now, I mean, this is something that mathematicians have picked up. First was Kevin Buzzard, and then Terence Tao, and then pretty much everyone in mathematics is using it. And what helped it is that once there was sufficiently large corpus of mathematical proofs written, AI people came and said, oh yeah, let's learn from that. And now AI for math is kind of an area on its own. This is not something that I'm working on, but I'm very happy that it exists because it promotes the fact that writing formal proofs by hand is no longer necessary, meaning all these tools that known to be hard to use, you actually don't need to learn how to use them because AI will do that for you. So CEDAR is an example of using Lean as not a mathematical framework, but as a framework in which you can embed a custom prover. And this is actually a very specialized prover for validating authorization policies and access control policies. So there are two implementations of CEDARs. One is in Rust and another is in Lean. They're fully compatible and both are developed by Amazon and used in production. So this sort of convinces that should convince the skeptics that Lean is also quite mature as a programming language. You can write a realistic system in it because big companies decided to do so. Okay, so when we implemented Whale and Lean, so what we aimed for is sort of this learning and this benefit curve. So you can start from something that allows you to check your system using concrete, or if you wish, explicit state model check, and then gradually go into decidable reasoning powered by SMT, and eventually graduating to interactive verification if so you need. But maybe you don't even need that. It's just nice to have all these things together. Okay, so what is VAIL? Well, VAIL is actually a very basic framework. It talks about distributed protocols, and actually any protocols just in terms of state transition systems. The simplest and the most basic abstraction, so think the set of states, also the infinite, the set of initial states, and the transitions. So we have they give a formal model for pretty much anything in computing. I mean, not everything is going to be nicely expressible. Sometimes you want to have a higher level of formalism, but this is the level of abstraction at which, for example, TLA plus operates to. So we have states, some of which are initial, and we have transitions, which are relations between states. So we can think about properties as something that is a superset of reachability relations, so which is a transitive closure of the transition relations, of the union of the transitions with regard to the initial state. And the property that holds on a reachable state, that's something that we refer to as system invariant. And particular kinds of invariants are those that are closed under the transition relations, which we call inductive invariants. The reason why inductive invariants are so important is that they are main proof vehicle for symbolic reasoning about state transition systems. So you verify safety properties effectively by induction. So it holds for initial states, and then it holds under transition. So this is how mathematical induction works. Okay, so as I mentioned, so we have safety and we have liveness, and I think I already had the slide. So, and okay, let's model some distributed protocols. So if you're familiar with TLA+, that's going to have a very similar vibe. So we are not going to have a dedicated primitive for sending or receiving messages or representing the network. We are just going to encode everything from the first principles. So we can encode multiple nodes as a, say, list or array of nodes. And each transition, okay, so it's going to be atomically performed by one node, but this is not necessarily the case. If you want to encode the synchronous protocol in which multiple nodes move in tandem, that's obviously you can also do. Okay, so let's try to encode this model using what effectively is the hello world of distributed protocols, a leader election in a ring topology. This is a very basic distributed protocol. It's not fault tolerant, so it assumes that none of the nodes fail. This is a protocol for multiple nodes that do not know of every single identity in the system to universally agree which one of them is a dedicated leader. What exactly means to be a leader and what this leader can do, it's not that important. So what is important is that the leader at some point knows that they are a leader, and every other node knows that they are not a leader. Okay, so let's see how this protocol works. So the reason why it's called ring is because the network topology is actually very simple. The node cannot communicate to every other node. It can only send messages to a dedicated node, which is its successor. And the way the network is arranged is that it forms a ring. So last important characteristic is that each node has a unique ID, and these IDs are totally ordered. They don't need to be consecutive, they don't have to be numbers, but there should be a total order relation. So having the ring topology and having the total order relation are just the two components that we need for this protocol to work. So this is how it works. So one node, every node sends its own ID to its successor. So for example, the node 1 sends its ID to 5, and in some random order, the nodes send messages, and in fact, some of the nodes might even start receiving messages while the others are still sending or like are about to send. So this is a synchronous system. The nodes actually act in some random order. Okay, so and when the node receives the message, it looks at the ID of the sender. And if the ID of the sender is smaller than its own ID, then it just mutes this message, so it doesn't do anything. But if the ID is larger than its own, then it transfers this message to its successor. So this is how it works. For example, this message from 1 to 5, I is going to be muted. So this message from 3 to 1 is going to be relayed because 3 is larger than 1, so 1 relays it to 5. And the same logic applies to other messages. So some messages just disappear, some messages transfer for longer, and eventually you probably imagine what is going to happen. So only the message from the node with the largest ID is going to survive to make the full round. So in this case, when the node receives the message from itself, it knows that it is the largest node. It's something, this is not the knowledge that it had from the very beginning, so it promotes itself to a leader. Importantly, any other node that has received the message from the larger node knows that it's not a leader. So at this point, we actually have, like, without equivocation, we know that there will be just one node that thinks that it's a leader. And this is a safety property that we want to establish. There are other safety properties, but this is the one that we want to focus. There is at most one leader. And even though this is simple, relatively simple, because we are very good at symbolically executing these protocols in our head, if you try to prove mathematically why exactly this gives you one leader, you realize that the argument is actually quite non-trivial. And before we come to this proof, let's look at how we can model this protocol in Veil. So I'm going to switch to the demo. So hopefully you can see my editor. So if not, please let me know. And what you are looking at is a lean file, except this is not what standard lean looks like. Standard lean looks more like OCaml or Haskell or functional language with some theorems sprinkled over it. What you look at is a number of macro definitions on top of lean. And many of them are domain specific to Veil. So effectively, they start with us starting this module, which starts from keyword Veil. And this is all imported from the package Veil, which actually has lots of the definitions, including the DSL and many others. The parts of the DSL, for example, allow us to define the components of our protocol. So for historical reasons, we are using words such as individual for scalar values. Otherwise, it's a function or occasional relation. So individual value, all nodes, it's just a list of all nodes. It's unspecified at this point because our protocol should work for any collection of the nodes. Next node is what should define the ring topology. At this point, it's not constrained to define a ring, so this is something that we will have to deal with later. And finally, just for the fun of it, we assume there might be arbitrary number of leaders, and obviously at some point we are going to say that, well, there should be at most one of them. We define the structure for messages, so this is just a structure as of lean, and the message has a payload, which is the ID of the node that had sent it, source, which the same thing, so there is a little bit of redundancy here, and the destination is where this message is heading to. Finally, since we're modeling everything from the first principle, we model all the messages in flight by the list. And again, this is just as simple as it is. There are probably 50 different ways to represent this protocol. This is just one of them. So now, when we move to defining the protocol, we say the set of initial states is just the state where we have no messages and we have no leaders. The evolution of the protocol is defined by actions, and you can think of actions as relations on state. And in fact, this is how they're encoded, but we give a more familiar imperative syntax. So this is actually a very nice operator. It's called Hilbert's choice operator. It says, let's pick n such that n is in the set of all nodes. By the way, lean is a strongly typed language, and so is Veil. So, and the reason why you don't see many type annotations, because many of these things are in for it. And what you see on the right, well, you don't really have to pay attention to it now, but this is effectively where you look at when you try to conduct a proof. We will come to that part later. So this procedure, send to next, is something that defines the logic of sending the message to the next in the ring topology. So we make the instance of the message, and if this message hasn't been sent yet, then we just append it to the soup of all messages currently in flight. And this is exactly this action of sending message to the next one. So that's not very interesting. The more interesting one is how we receive the message. We randomly pick message from everything available, and we look at where this message is heading to. So we remove this message from the messages currently in flight, and we look if this message came from a certain node, and this node happens to be us, so the destination, and we are not the leader yet, then we just make ourselves a leader by appending us, it's our own ID n, to the list of leaders. And this is exactly this action when we become a leader. So finally, if we receive the message from someone who is larger, or at least as large as us, so this is actually be a strict inequality, we send it to the next. So this is the whole protocol. It's very similar to how you would define it in TLA+.
Excuse me, please.
Excuse me, please. You are
Did you
excused.
say
Yes.
randomly or non-deterministically?
I said randomly, but probably you want to hear non-deterministically. I'm not sure
Okay,
that's very
okay.
important in this case, but maybe you can explain me why this might be important.
Well, because random program with randomness is another than non-deterministic program. Thank you.
Okay.
Ilya, I have a question also about
Yes.
the arbitrary message that you. So, do we need to worry about fairness or some such, or is it that Lean will automatically consider all sequences of messages?
Great question. Okay. Should we worry about fairness? Let me answer actually two parts of it. First of all, the second part, when you run this protocol, and I'm going to show you in a minute how you can run this protocol, we actually made sure that every message will be exercised. So, and this is something that we have proven, so that there will be no missed choices from the non-deterministic selection. When we talk about fairness, this is actually something that only matters if we want our protocol to be live. So if you want to show that certain things eventually happen. So this is quite interesting, and I'm not going to show it in this talk, but there is a way to prove liveness properties, as in things eventually happen in Veil, in which case you can put constraints on saying that certain action that is enabled eventually will be taken. So if basically this way you can specify that any conceivable message that will be at some point here will be eventually delivered, and you can express that symbolically.
Yeah, thank you.
Very well. Yeah, good question. This is actually highly non, and actually this is actually something highly non-trivial to implement, because the crazy thing about this non-deterministic choice operator is that it has very simple symbolic semantics. So if you want to verify a program that non-deterministically picks a certain value, well, depending on whether like your non-determinism is angelic or demonic, you pick either existential or universal quantification. So you say that either exists a message such that something holds, or for any message, everything like something holds. And symbolically, just like as simple as swapping quantifiers. However, if you want to execute that, you actually need to have an enumerator that will take all the messages that satisfy this particular predicate. And I hope you can appreciate the fact that this is actually not this is not a keyword. So M in messages is just an arbitrary predicate, which by the way doesn't have to be decidable. Arbitrary predicate that says what kind of messages we are looking at. So and the magic of the implementation is that obviously in order for that to be computable, this predicate needs to be decidable. And what is happening under the hood, that Veil synthesizes the decidable version of these properties, which is then used as a filter when enumerating all the messages that we want to non-deterministically pick. I keep saying messages, but in fact it works for any non-deterministic choice over a finite domain. Yes, so someone has a question.
Yeah, I think your comment answered it, because I was going to ask, well, we also have infinite spaces for which membership is decidable. So can I have an infinite space of messages? And I guess not, right?
Yeah, well, not in this case, but I don't know why practically that would be very relevant, but that's an interesting question. We never needed it. Yes.
Yeah, I mean, it's possible to have it in protocols like the DNS search, where you are going over strings or queries where the domains can repeatedly keep changing. So now you have arbitrary strings, which are your messages being sent around, and that would be potentially infinite space. But yeah, it's irrelevant for this conversation. So
no, that's a good remark. Thank you. I wasn't aware of that. I mean, one thing that I want to emphasize that this is just a way to model non-determinism in a protocol. I mean, like if you want to determinize your choice, you can just write a plain Lean function that will pick whatever you want from your possibly infinite set. Okay, so interesting part, we have a safety property, and we are going to run model checker. So I already run it here, so let me just rerun it. And you will see the result here. And by the way, this is not something that Lean gives you by default. So those of you who have experience with TLC might appreciate the fact that this actually looks very similar to TLC, and this is something that we have implemented. We also have proven the model checker to be sound and complete with regard to symbolic semantics, but that's besides the point. Okay, so let's break the protocol. Let's remove this check and we run that. So now you will see that very quickly it has found an error, and very much in the tradition of explicit state model checkers, it also give you a counterexample in the form of the trace. So these are the transitions with these values of non-deterministically picked messages that have to be taken in order to reach something, the state where we have two leaders. And this is just one of them. So, and yeah, so this is how people use model checkers. The model checker, like explicit state model checkers, they are very powerful things. So in fact, you can use them not just for checking the finite instances for safety properties, you can also use them for reachability checking. It's actually really fun examples. I wonder why it has reset me to the beginning of it. Okay, so yeah, so we had plenty of questions. I'm gonna stop again, but after that, but this is an example that some of you might know. This is from Lampert's lectures, and this is
Ilya, a question.
Yes, please.
So what was the proof technique for that for this ring redirection? I mean,
so we haven't yet seen the proof. So we have only tested the protocol so far. So we are now at the stage of TLA plus. We are about to go further to the stage of IB and other tools. So this is all testing so far.
Because this is an infinite state system.
It is infinite state system by the fact that we have infinitely many ways to instantiate these components. But so far we only picked the finite, like concrete finite instances, which give us finite state space of that many states. Make sense?
So what does it use like an inductive invariant? Or?
Again, the inductive invariant is something that is an artifact of a proof by induction, which lives in the symbolic reasoning. So far, this is as simple as making everything concrete and running this effectively as a breadth first traversal through the very finite state space of the system. There is no proof. It's a glorified testing.
Oh, I see. So it's doing a bounded search, is it?
Exactly. Yes.
Oh, I see. I thought you did a model checking. Okay, so the model checking is just a bounded model checking.
Well, I mean, again, I don't want to get into the terminology holy war here, because when I say model checking, I mean explicit state model checking. If we think about and what you probably call by bounded model checking, I call it symbolic model checking. So something that compiles the system to a formula and then checks satisfiability or unsatisfiability of this formula. We will see that too. But to me, that lives in this bounded model checking lives in the symbolic world, and explicit model checking is testing. Okay. Are we good on that?
Yeah.
Yeah, good. All right, so moving on. So explicit state model checking. Some of you might know this example. It's actually a very famous one, popularized by Lamport after the movie Die Hard 3, where the two characters need to disarm a bomb by having a 5-gallon and 3-gallon jugs and having to fill the larger gallon with exactly 4 gallons of water. And the way to solve this with an explicit state model checker is obviously to encode it as a state transition system where the state are just these two natural numbers representing the amount of water in each of the gallons. And then initially we have 0 gallons. And then each transition tells us what is happening if we do the respective action with our system. The nice thing is that if we say that our safety property is that there is never the state in which we have 4 gallons in a large jar, then if you run the model checker, okay, so we have a special flag, so it won't complain in red, it will just basically negate the result. Then it gives a concrete counterexample, which is this trace that exactly leads to the state when we have 4 in the large jar. And this is a solution of the problem. So another one that people like is this classical one, which I think everyone knows since childhood, about the wolf, the cabbage, and the goat, whom you need to move across the river. All right, so enough with the testing. So let's graduate to the symbolic world. Probably need to speed up a little bit because I definitely am running out of time. So yeah, something is wrong with my presentation software because it doesn't go full screen. So let me just tell you. So we now want to do symbolic reasoning. And symbolic reasoning, and again, this is where people really kind of have feelings about how to call particular ways to symbolically reason the system. Symbolic model checking, bounded model checking. So yeah, I'm never sure like what's the right terminology in particular situation. For me, symbolic testing is something that compiles the system to a formula, but doesn't require you to prove, to establish an inductive invariant. So effectively, we do what CBMC does or CLI does. So it's you can think of symbolic execution. It's a finite unrolling of the system states and checking that this unrolling for arbitrary number of nodes doesn't violate certain property. Symbolic verification is effectively verifying a program with a loop, and here we have a program with a loop. It's implicit. It's taking all the actions in perpetuity by finding a loop invariant or an inductive invariant. So this is the difference between symbolic or bounded model checking, aka symbolic testing, and symbolic verification. So let me just very quickly, so symbolic or bounded model checking effectively for me, compiling the property of interest, P, and the description of the system into either this first formula, and the first formula basically has to do with whether the certain state is reachable. Can we, in a finite number of steps, can we reach a state that satisfies this property? And the difference between that and explicit state model checking is that we only keep the number of steps concrete, and everything else is now symbolic. So arbitrary number of nodes. And this is about proving safety up to a number of steps. Saying, okay, for any intermediate states and that many k steps, certain property holds, or typically the negation of certain property holds. So which P means that thing. So, okay, when we try to verify a system, we actually don't want to fix this k. We want to show that it holds for arbitrary k, and that means proof by induction. So in this case, we in the classical inductive proof, we show that our property is something that is implied by a stronger one, which is called inductive invariant. This inductive invariant is satisfied initially, and then this inductive invariant, well, effectively is preserved by induction step, or it's closed by all the transitions. And these are effectively the two proof modes. So to show these proof modes, I'm going to switch back to my example, but some of you who try to implement SMT-based verifiers for programs that use lists and natural numbers might know that these particular data types, they're just too rich. They have too many intrinsics. So they are not very well representable in first-order logic. So if you try to build formulas with them, SMT solvers will most likely time out. So this is where we start learning about abstraction and the fact that sometimes you really want to hide the details of your data types behind what's called uninterpreted data types, uninterpreted sorts, and things such as an interpreted function. So you don't know what these functions do. You only have some properties. The nice thing about Veil is it actually allows you to accommodate both styles, and even, which I'm not going to show, prove the refinement between more abstract and more concrete view. Okay, someone asked me about abstraction, so maybe that would be a good discussion to have at this point. So I'm going to show more abstract version of the same protocol, which is also encoded in Veil. So here, instead of concrete data types, I'm going to represent leaders as just a relation. So some nodes are leaders, some are not. And all the messages in flight pending, this is just a relation between the node who sent it and the node that is about to receive it. I don't know anything about what the node is. It's uninterpreted sort. The only thing I know is which theories it satisfies or which axioms hold true. So nodes can be integers, they can be strings, but they need to be totally ordered. And the nice thing that Lean gives us the mechanism of type classes, the same as Haskell, that allows us to specify properties in addition to operations. So total order is something that comes with the binary relation that is reflective, transitive, antisymmetric, and total. So that's a total order, and between is something that effectively specifies the ring topology. I'm not going to explain all these components. You can believe me that actually this is the ring topology. So now the system becomes very easy to define. You can recognize the same properties, except now, so capital means for every node n, initially the leadership relationship is false, and every pair and pending is the relation that is empty. So now we have send and receive, which are very similar in its shape, except instead of using the non-deterministic choice, I just pass these things as argument. This is equivalent. It means that this relation will be exercised for any combination and next, such that this precondition is satisfied, and this precondition effectively says that n is predecessor of next. Okay, will be happy to explain more about this syntax, but now just bear with me and you will have to believe me that this is the same protocol. Okay, now let's do something interesting. So the nice thing is that despite this abstract nature of this protocol, if we provide a concrete instance of the node data type, Lean will first prove that it satisfies all these axioms, and then we can plug it and use it for concrete state model checking. And this is again the same model checking. So for example, if we deliberately mess up our protocol, we'll see how this breaks. And this is again, this is not a proof, this is a checking. But now let's prove something interesting. So let me mess up with this protocol and make it safe, but very useless. So I'm just gonna make it so that no one ever becomes the leader. And this is exactly where symbolic testing or bounded model checking becomes very useful. So effectively what has happened now, we can ask questions. Can it be, so if we take any three actions for some unspecified number of nodes, you figure, like SMT solver, figure out, can we have that situation where we have a leader elected in this protocol? And you see, it says like, no, this is actually an unsatisfiable query. No satisfying trace exists. And if I restore that back, then this passes. The beauty of it is that what effectively is happening is that I'm not just attaching a solver as a tool. What is happening is that I compiling that to a Lean theorem. It's a very ugly theorem, but this is an important part. So whenever I deal with proving some facts in Veil, it always goes through Lean. So every fact that I'm proving is a Lean theorem. And how exactly I'm proving it, that's up to me. So if I want to prove it by using SMT solver and getting unsat, that's great. If I want to prove it interactively by writing a proof script or using AI, that's also fine. And this is actually the key distinction of this methodology. We no longer build verifiers around a particular backend, such as a certain decision procedure or an SMT solver. We build it around Lean. And Lean effectively serves as an intermediate representation for the statements that we want to prove. And these statements is something that Veil produces. Okay, so I'm gonna skip to this part and now come to the proper deductive verification. So we want to show that this property is actually like holds for any reachable states. And the proof is by induction. Let me pin this. Okay, so what is happening, and again, this is the front end that we have compiled, we produce a bunch of what's called verification conditions that correspond to proving these statements. So most of them hold, but one doesn't. And those of you who are familiar with proofs by induction, you might recognize that this is actually a counterexample to induction. So we have a pre-state that satisfies all invariants, and then we have a post-state that doesn't satisfy the invariant. And typically the way it works, and like those of you who know how invariant inference algorithms such as Houdini work can recognize that, you look at this and say, oh, look, we have a message from 0 to 0 and we have a message from 1 to 1. That's not possible. There might be at most one message from the node to itself, and that should be a message from the largest node to itself. So, and this is how you strengthen the invariant based on the counterexample to induction. So you go and you figure out saying that if there is a message from node L to L, then it better be the largest node. So any other node is larger than this. So you plug this invariant back, and now you see we have more verification conditions to prove, but we're still not there. So we got more counterexamples to induction. So this is a process where usually humans get creative and they come up with heuristics, and papers on tools such as Houdini are published. Nowadays, we live in a fantastic time because you can give the textual representation of your counterexamples to AI, and it will do a pretty good job inferring invariants. So believe it or not, invariant inference, especially with the decidable oracle, the one that gives you answer immediately and doesn't require you to write a proof, it's actually, like, it works really well. So again, obviously I had this invariance before, so I keep adding more and more, and eventually my invariant happens to be strong enough so all the verification conditions are proven, and I'm happy, and this means my protocol now is verified. So there is a small wrinkle here that it says, I'm trusting the SMT solver for 12 goals, and those of you who are very strict on trusting the provers might ask, okay, but you believe the SMT solver. Well, in fact, I don't have to, because this is just for speed. And what I can do is I can switch on what's called proof reconstruction, and I can get the Lean proof back from the SMT solver. It will just make the process 5 times slower. Okay, so basically now we went through the whole cycle. We went through seeing the TLA plus explicit state model checking. we have gone through looking at seeing the bounded model checking, and finally we have seen the deductive proof. The only thing that we haven't seen is what effectively people use Lean for. And people use Lean for interactive proofs. And this is something that I'm going to show very briefly by going back to this protocol, which actually does not have all the invariants. I'm going to type that here. And let me just unpin this thing here. Yeah, and you see here I actually have an outcome when the invariant hasn't been disproven, but it just says error. And what it means is that we actually hit a statement that SMT solver couldn't prove. But luckily, we are in an interactive proof assistant. And the nice thing about the interactive proof assistant is that you can prove things interactively. This is still not going to be provable. I don't have the whole inductive invariant here, but what I can do, I can click here and I get a statement of a theorem. And this is effectively a theorem as mathematicians see in Lean. And in fact, this is actually such, I mean, okay, the statement looks scary because there's a lot of generic programming here, but in fact, it's so simple that our default tactic just proves it. Okay, let me get a different statement. So the nice thing is now if I rerun this verification from scratch, you will see that where there was this statement that I failed to prove, let's make sure we reach this point, we will see that this statement is now, it doesn't show here, but typically these statements are shown to be proven interactively, so you can just plug your proof here. I think there is a problem with updating the variable. The point is that if you cannot prove something by SMT, you don't have to. You can go to the interactive proof mode and prove the statement the same way as mathematicians do. Okay, so that's been quite a mouthful, so maybe I'll just pause for a couple of minutes here, given that I'm also out of time, and take questions, and then I will very briefly conclude. Any questions about this? Can someone say something so I would know that I haven't lost connection here?
Yeah, I don't think there are any questions, Ilya.
Okay, good. All right, let's go back and like very quickly I conclude. So this is something that we have benchmarked on a number of protocols. The performance is worse, or at least it used to be worse. Now it's better than some state-of-the-art tools. So this is as of last year, but we haven't rerun the benchmark suite. The interesting part is that people use this hybrid combination of tools to verify distributed protocols. And this is something that we could have done in Lean. And there was an interesting discovery. So for example, there was this protocol that was verified in the combination of SMT-based to Ivy and interactive to COC or ROC nowadays. And the interesting, and the part about this protocol is that it actually split the property to be proven to two conjuncts. One conjunct has been proven using SMT and Ivy, and then it has been ported to ROC as an axiom where this implication has been proven. And there's nothing wrong with that. This is actually a legit way to decompose the proof obligation and establish it, but well, these are very different tools with very different syntax. So what happened is that, in fact, there was a bug there. So because this is what syntax of Ivy looks like, and this is what syntax of ROC looks like. And just to show you what was the difference, so you see that in Ivy, they show that the property holds for something that is a successor of P, but in ROC, they took it as an axiom that something holds for P itself, not a successor. Again, this is highly example specific, but basically they had a wrong assumption for the second part of the proof, and it went unnoticed because that was taken as an axiom. Obviously, this is something that doesn't happen when you are within the same theorem prover. And this is one of the advantages of building your verifier as a library in a general proof assistant. Okay, so Veil is the tool that I have shown, and it's let's see why do I have this thing here? I don't know. So it's some artifact. So Veil is under very active development. This is actually just one of the verifiers that we have built on top of Lean. We also have others for imperative programs, and we have another one for security protocols, and they're all kind of talk to each other, so you can verify different parts of your program using different verifiers. So we also have support for liveness. Actually, I have this blog. Well, my lab has this blog called Proofs and Intuition, intuitions. So there's a number of posts, including VL. So if you want to have like a blog post version of this talk, then there is this one, but there's also one that Chuan, my student, and myself, we have wrote very recently, which discusses how to prove liveness in VL and how to use LTL specifications to specify fairness and eventuality of certain things in the system. So there are quite a few features that are still missing, such like, for example, we don't have like decomposition using model system, and we don't have proof for refinement in a full-blown sense, but this is all that is coming. Okay, so to take away, so what I want you to remember from this talk is that, well, I've shown you to verify distributed protocols in this multi-modal mode, combining automated and interactive modes, and also combining the explicit state model checking and symbolic verification techniques. And importantly, although this is not something that I emphasize, this tool itself is proven sound, because verifier is just something that produces theorems about your system. Whether those are the right theorems to prove, well, that's not clear. That depends on whether your verifier itself is verified. And well, worry not, because well actually is verified itself as a program. As a user, you don't have to see it, you don't have to worry it, it's just there. And I think it's a nice property to have about the prover, that your prover is actually sound. So it has acceptable performance, actually pretty good performance now for first-order logic by using SMT solvers, but it also provides seamless integrations with higher-order properties through the interactive proof mode. So we have a bunch of papers about that, one from the CAF last year and one from the Daphne this year, and also there is this blog which you are welcome to check. This is all I have for today, and thank you so much for your attention.
Thanks, Ilya. Thanks for a great talk. Are there any questions?
Yes, I think there is a question.
Yeah, go ahead. Yeah.
Mm-hmm.
So my question was about infinite state systems, because I think, so in your modeling, it's possible to model states as natural numbers, and of course, transitions could just be successive functions, and you could inherently model infinite state systems. But would that allow easy modeling of, say, push-down systems or asynchronous message passing models?
Oh, yeah, absolutely. Yeah.
Yeah. So it would then be possible to have automated verification of push-down systems, because they have a different kind of saturation. Not quite.
Well, okay. So I know that people who study the scalability and automata theory, they this is a very sensitive topic. So what I'm saying is that you can model push-down automata, and you can model infinite state systems. I did not promise that you will have automated decision procedure for these properties, because, well, you know, you have like two stacks that's already Turing machine, right? So what you can do is that you can express that, and you can still express the safety and the liveness properties. And what I give you is a vehicle to prove those properties. But I'm not gonna, I mean, obviously I'm not gonna go against like mathematically proven impossibility results. I'm not gonna give you push button decision procedure. You can write your proof interactively.
Okay, I see. Because so the reason I asked this was, yeah, well, I suppose it's, so essentially we have to model our own verification procedures in effect by writing them within the framework. Right? Like
well, I mean, okay, so what kind of problem, what kind of verification procedure do you have in mind? So because that might help me to answer that.
So let's say you have a single push-down system with a single stack, so not multiple stacks, and you want to check the reachability property of a certain control state. The way it usually goes is not by unfolding the transitions, but rather some sort of a middle out procedure where you have a push and you balance it with a pop.
Yeah, and some sort of the reachability. Yeah, okay.
Yeah, and here I think this is not very inherent to unfolding, so it wouldn't quite work with the existing ways that are established.
Yeah. Okay, so good question. Let me unfold it. So what we have gives you a way, basically gives you a domain-specific language to define state transition systems, possibly infinite state. And it also gives you a number of proof principles for which we have dedicated support. And one of these proof principles are proofs by induction using, like, by finding an inductive hypothesis, aka inductive invariant. However, I didn't say that this is just monolithic and you cannot do anything else. So you can still take the part that gives you a domain-specific language, like to define your state machine. You can always define stack. I mean, like, you've seen me using lists, so you can just define stacks here, and you can get the definition of the state machine from here and define your own decision procedures and your own properties. So yeah, so this is like, obviously, if you're willing to do that, we will be more than happy to tell you how to plug your decision procedure into Veil. So we have an example for that. That's like the support for Linus proofs. We only added it like a year and a half after the initial system has been developed by effectively taking the trace model that is produced by the descriptions of the systems, plugging it into the semantics of LTL formulas, and proving a bunch of like eventuality, like Lamport's, like weakest fairness rules, and using them to prove Linus.
Yeah, I have actually checked out your blog post.
Very well, yeah.
So, okay, I see. Thanks.
So yeah, I had one question about so I mean, like, to prove these systems correct, typically one has to come up with an inductive invariant. I mean, that's one
in the full
popular way to do
generality,
it.
yes, that is the case.
Is there any support for coming up with that, like, learning an inductive invariant?
We used to have some versions of classical like UPDR and these techniques that effectively are fancy heuristics for generalizing counterexamples to induction. I'm gonna say something that might sound controversial. I think this research field is largely dead now, because AI is just very good. So I mean, theoretically, I think there's like very interesting cases to study. Practically, like, LLMs are very good in generalizing counterexamples, and the only thing that you need to give them is a quick way to iterate with an oracle. So this is why it's interesting that you can have the system which is effectively compiles to something like EPR, so you have like guaranteed decidability, and you can iterate quickly until you infer the invariant. But Veil itself, being just a library in Lean, it's much more general, so it's very easy to write something that is not an EPR, not even in first order logic. In this case, there are interesting things that you can play. For example, you can do something like decidable specification inference, again using AI, and then do the invariant inference with this abstraction, and then try to backport your invariance into the actual model. It might sound kind of controversial, but we have actually done that. So we have taken Paxos, which was written by Lamport himself in TLA+, just translated it into Veil in the most like one-to-one correspondence, and then went through this round of first kind of trying to use AI to get the model which compiles to EPR, do the invariant inference there, transplant the invariance back to the original model, and now we have almost guaranteed inductive invariance, except we don't have a proof. But since we already like have a lot of evidence that these are likely to be proper inductive invariants, we can use AI to write proofs for their inductivity interactively. So lots of interesting things to explore. I think the decision procedures still are very important, but the inference procedures maybe not as much.
And one last question. So usually in distributed systems, an important property is something like this eventual consistency. Do you have any support for that in Veil? Or?
Yes, so that's what I've mentioned, but sadly I don't have a good demo for that. So this, so eventual consistency is a Linus property. So like certain things eventually happen. And for that, there are just different proof principles. So typically you pick an formalism like LTL to describe that, and LTL comes with a number of rules that allow you to reason about the consequence. And what Veil gives you is a way to inject the definition of your system into LTL-powered proof system. And then you can write, so we don't have, actually, I don't think anyone has automation for these general proofs in LTL. If someone knows about them, please let me know, because I would be very curious to implement it here. But you can still, like, what we can give you is a proof language, which again is just an embedding in Lean to prove properties like eventual consistency interactively.
Okay. So if there are no more questions, let's thank Ilya. Ilya, thanks again for a great talk.
All right. Yeah. Thank you so much. Okay. Have a nice evening. Bye.
Okay. Yeah. Bye. Bye.